Have you ever wondered how we're able to measure the height of buildings or maybe the height of mountains or things like that? It's not like we actually use a giant ruler that can measure in thousands of feet or anything like that. What they actually use is the geometric mean. Okay, and we're going to show you how that's used. And then when you work on your problems tomorrow, you'll see a real life example of that. But the geometric mean is the positive square root of the product of two numbers. So that's just what it is. And then we're going to use it with right triangles here, and I'll show you how that's used to measure heights. So geometric mean, positive square root, product of two numbers. So I got two numbers here, A and B. If I'm going to take the geometric mean of A and B, all I would do is square root, multiply them and square root. Right? The product, multiply, and then we square it up. Pretty easy. That's all we got to do. So if I wanted to find the geometric mean, all I got to do is multiply the two numbers. So 5 times 45 and take the square root. Well, let's look at this for a second. If I take 5 times 45, I end up with 225. Well, let's write these in simplified radical form. This one's kind of nice because 225 is a perfect square. So we actually end up with 15. Okay, but if I look at the next one, if I found the geometric mean of 12 and 15, well, 12 times 15 is 180. So what I don't want to do is don't take your calculator and just take the square root of 180 and then say 13.4. Don't do that, okay? That's too easy. Let's challenge ourselves. Let's go back to algebra. How do we simplify a radical? Well, we got to look for perfect square factors of 180. So what's a perfect square that goes into 180? First one I can think of is, I know 9 does. Well, 9 times 20 goes in there. But then if I think about that, 20 also has a perfect square factor, doesn't it? 4 times 5. So there's got to be something bigger than 9 that goes into 180. Let's try some bigger numbers. Let's go 180 divided by maybe 36. Oh, that works out. 36 is a perfect square, so 36 times 5. So really remember I have the square root of 36 times 5, and I can break this up just like that. And the square root of 36 is 6, so I have 6 times the square root of 5. So let's challenge ourselves a little bit, and let's get these in simplified radical form. That's some good review for us using our algebra, yeah, instead of getting a decimal. We got a couple theorems here. If the altitude is drawn to the hypotenuse of a right triangle, so for example, BD is my altitude here, the two triangles formed are similar to the original and to each other. So for example, it's just saying my triangle ABC, my big triangle ABC, is similar to each of the little ones that it made. Well, let's think about this. ABC would be similar to what? If I look at this small one right here, how would I write that? Triangle, well, A in the big triangle would be congruent to which angle in, I think also angle A, right? In the small one. And then B is the right angle in the big triangle, right here. And the right angle in the little triangle here is ADB. So it matches up with D, and then we're left with B. So there's my small triangle right there. And that's also similar to this guy as well. And let's match up our vertices. So A would be similar to what angle in this one? I would say down here with B. And D is the right angle. Right angles are all in the middle here. And C. So all three triangles are similar. The big one to each of the small ones that it created. That's only if I draw an altitude to the hypotenuse. Altitude from the right angle to the hypotenuse. Okay? Doesn't work for any of the other altitudes, just that one. The other theorem that we're going to use is our geometric mean theorem, our altitude theorem. So the length of the altitude is the geometric mean between the lengths of the two separated segments. So if I look, here's an altitude called H, and it splits that hypotenuse into two segments, X and Y. X and Y. Well, to find H, I just take the geometric mean between X and Y. And how do I do the geometric mean? I multiply them, and I take the square root. So to find h, to find that altitude, I would just take the square root of x times y. And we're going to use that here shortly. We have one other theorem called the Leg Theorem. This one's a little more complicated, but once we get it set up, it should look a little nicer. So the length of a leg is the geometric mean between the length of the hypotenuse and the segment of the hypotenuse adjacent to that leg. So that's kind of confusing. Let's think about this. So basically, the length of a leg, so here would be A and B would be my two legs of the big triangle, is the geometric mean between the length of the hypotenuse. Well, what's the length of the hypotenuse? C, isn't it? And the segment of the hypotenuse adjacent to that leg. So if I'm looking at A, the segment adjacent would be X. If I'm looking at B, the segment adjacent would be Y. So here's our two equations I come up with. If I'm solving for A, it says the length of the leg is the geometric mean between the hypotenuse, which is C, and the leg adjacent, the segment adjacent, which is X. So if we take a look, it's basically segment times the whole side, the geometric mean between those two, and that will equal that leg. So they kind of match up. That one's a little more confusing. If I'm looking at the other one, to find B, if I want to find this leg, I take the segment adjacent times the hypotenuse of the big triangle, and I square root right down here to find that leg. Okay, those ones are a little bit harder to come up with. The altitude's much easier. The other theorem's much easier. Let's go ahead and use all these things here now. So let's find C, D, and E. Well, the first theorem, much easier, right? To find the altitude. Because to find the altitude, it's just the geometric mean between the two separated segments. So the square root between 6 times 24. And if I take 6 times 24, I end up with 144. And the square root of 144, we know that's a perfect square, so E is 12. So done with that guy. Well, if I really wanted to, I could use the Pythagorean theorem to find D and C, because I have all right triangles, don't I? Let's not do that. Let's actually use our geometric means. Let's find our rules for the geometric means. So let's go ahead and let's solve for D right away. So if I'm looking at D, D is going to equal, remember, it's the geometric mean between the entire hypotenuse, so this whole thing, which is 30, because I got to add those up, and the segment it's adjacent to, 6. So 30 times 6. And if I take 30 times 6, I got the square root of 180. And we just did that just a bit ago. Perfect square factors of 180 are 36 times 5. So D equals, well, the square root of 36 is 6, and the square root of 5 is just the square root of 5. Can't simplify. So let's keep them in simplified radical form. And lastly, let's go ahead and look at C here. So to solve for C, it's the geometric mean between, right, the whole hypotenuse and the segment adjacent, which is 24. So 30 times 24. And 30 times 24 gives us 720. And let's try taking the square root of 720 and see if it's a perfect square. It is not. So are there perfect square factors of 720? Well, let's see. Let's just start dividing some. About 36. 36 and 20. But 20 also has perfect square factors, right? 4 and 5. So I know there's a bigger one than 36. So let's keep trying some even ones here. What about 64? Let's try 64. 64 does not work. Let's try 100 doesn't work. What about 144? 144 works. So 144 times 5, and the square root of 144 is 12, and the square root of 5 is just 5. And we're done. That's what C equals. Okay, so get it in simplified radical form. No decimals today. All right, lastly, there's two ways to start this guy. A lot of people are going to want to just do Pythagorean theorem and solve for y, right? Taking 4 squared plus y squared equals 12 squared. That's one way I could have done it. Okay, I'm not going to do it that way. Right? Using your past knowledge, that's great. I like that. let's try something different here. I'm going to go ahead and I can't find x yet because I don't even know anything else with that other triangle over there. I don't know what z and y are yet, but I can find z. I can find z. How could I bring z into play? Well, I couldn't do the geometric mean of the altitude because that would be y equals the square root of 4 times z. Well, I need to know what either y or z is, so I can't do that yet. Well, how else could I solve for z? How could I else bring in z into play? Well, think about this. I know that 12, right? That leg equals the geometric mean between the entire hypotenuse here and the segment adjacent. So it's really 4, that segment adjacent, times, well, how big is that whole side? It's really z plus 4, isn't it? Just adding those two together. Well, I got to put that in parentheses, z plus 4. Well, I can solve this. Well, I'm going to go ahead and simplify inside that radical there. Square root 4z plus 16, then distributed. Well, I want to solve for z, so I got to get it by itself. I always do the inverse of what's being done. Got to get rid of this square root. Well, the inverse of square rooting is squaring. Whatever I do to one side, I do to the other. Going back to our algebra last year, so 144 equals, well, these guys cancel each other. So 4z plus 16. Subtract 16 from both sides, and I got 128 equals 4z. And then we divide by 4. And z equals 32. There we go. See, I can solve for z, given this information. So I'm going to go ahead and write that in. Z is 32. Well, now I can plug this into that first one I had. I'm going to put in 32 for z over here when I was trying to solve for y. So 4 times 32. Well, and 4 times 32 gives me 128. Which is not a perfect square. Does it have perfect square factors? Well, let's give it a shot. I can divide by 4. I can get something bigger than that. Let's try dividing by 16. I can do something bigger than that. Let's try 36. Doesn't work. 120. Oh, 64, right? Isn't that half of it? 64 is a perfect square, so 64 times 2. So square root of 64 is 8, and the square root of 2 is just 2. Square root of 2. Can't do anything with that. Very good. And we still got one left. I got to solve for x. Well, now that I know that y, well, I don't even need to use this, but I'm going to write it in there. So to solve for x, that's the geometric mean between, right, the entire hypotenuse, which we know is 36 now, right? 32 plus 4. And the side that's adjacent, which is 32. So it's the square root, geometric mean of those two sides, so 36 times 32. So x equals the square root of 36 times 32, which is 1152. That's a big number. Let's see if that's a perfect square. It is not. In this case, that's a pretty big number. I don't mind if you round this guy. So we'll say approximately 33.9. I'm okay with that. For the most part, anything under 400 or so, we should be able to do perfect square factors and simplify. So there you go. Using that geometric mean. A couple different theorems with that.